Welcome to The Explainer. Today, we're taking apart an absolute marvel of modern engineering, the mighty industrial gas turbine. Now, if you've ever stood near one of these beasts, you already know they push out a massive amount of horsepower. But how do they actually do it? I mean, how are they generating so much power from such a relatively compact footprint? Well, today, we're going to peel back the layers and break down the foundational thermodynamics and structural architecture that makes this whole machine tick. All right, let's jump right in. The engine humming inside that massive steel enclosure out on your site? Mechanically speaking, it's a jet engine. Seriously, it's built for a totally different job, but its DNA is absolutely born in the sky. If you were to strip away the aerodynamic nacelle of a commercial jetliner and you just bolt that exact same engine to a generator on a concrete pad instead of, an airplane wing, you essentially have the exact machine we're looking at today. It's the same fundamental engine, just adapted for an incredibly demanding industrial purpose. So, what's its primary mission? This machine's sole reason for existing is to convert a fuel's chemical energy into rotating shaft power. And crucially, it needs to do it faster and lighter than practically anything else on Earth. Think about it. When you're out on an offshore oil platform, or you're trying to squeeze a fast response power plant into a really tight urban grid, weight and footprint are your ultimate constraints. Pound for pound, literally nothing converts fuel into usable shaft power more efficiently than a gas turbine. That makes it the absolute perfect hero for environments where a massive traditional power plant simply wouldn't fit, or would just weigh way too much. To really understand how it achieves this, we need to look at how it breathes. This operates on the Brayton cycle. Now, you've probably heard the phrase suck, squeeze, bang, blow used for car engines, right? Intake, compression, ignition, exhaust. Well, with our gas turbine, it's very similar, but with one massive difference. It continuously and simultaneously pulls air in the front, squeezes it incredibly hard in the compressor, burns fuel in that squeezed air, and then blasts the expanding hot gases at the back. All four of these stages are happening at the exact same time, just in different physical sections of the machine. To put that in perspective, think about a standard reciprocating diesel piston engine, like you'd find in a heavy truck. A piston engine breathes in intermittent pulses. It intakes, compresses, fires, exhausts, over and over, delivering power in distinct, violent pulses that have to be smoothed out by a massive heavy flywheel. But our gas turbine, it never stops breathing. Because air is constantly entering the front and exhaust is constantly leaving the rear, it delivers this incredibly smooth, continuous, vibration-free power. Every single stage is happening at every single instant. Moving into Section 1, power-to-weight ratio. Here, we're talking about trading raw size for incredible efficiency and speed. In the industry, we call these jet engine derivatives aeroderivative turbines, and the whole philosophy here is trading bulky size for an elite power-to-weight ratio. And when we look at the numbers, you can see our aeroderivative unit is punching way above its weight class. A colossal heavy frame industrial turbine might produce 200 to over 500 megawatts of baseload power, sure, but it requires a massive purpose-built foundation and weighs hundreds of tons. Our aeroderivative unit, on the other hand, delivers a really solid 30 to 60 megawatts from a package light enough to literally be craned onto a ship. Plus, it achieves higher thermal efficiency, up to 43%, and boasts a massive compression ratio of up to 30-1. That's nearly double the compression of some heavy frame units. But a quick word of warning here. Don't mistake a smaller, highly efficient engine for one that's less demanding to operate. That 30-1 compression ratio and the extreme rotational speeds you need to achieve it mean there are incredibly tight field tolerances inside this machine. I'm talking virtually zero margin for error during operation and maintenance. The air is being squeezed so intensely, and the parts are moving so incredibly fast, that even microscopic deviations can lead to catastrophic damage. So smaller size definitely means higher precision. Because of this continuous breathing and super lightweight design, this machine actually has a bit of a superpower: extreme agility. This compact package can go from a completely dead cold idle to pushing over 30 megawatts of synchronized power to the grid in just a matter of minutes. When a city's power demand suddenly spikes, or the wind drops off at a wind farm, these aeroderivative units are basically the fast response cavalry. They rush in to stabilize the grid instantly, and they do it without any of the violent shaking you'd get from a piston engine of the same size. Okay, let's lean in for a quick check, because this is where the engineering gets wonderfully clever. Think about this for a second. The electrical generator bolted to the back of this engine absolutely has to hold a fixed, rock-steady 3,000 or 3,600 RPM to match the electrical grid.
but the hot core of our jet engine needs to spin past 10,000 RPM to produce the right amount of power. So how exactly are they connected? Because if they share a solid metal shaft, someone's going to have a really bad day and something is going to break.
The answer is they absolutely cannot share a shaft. There have to be two completely independent, decoupled rotating systems inside that single steel casing. The front section, the gas generator that sucks, squeezes, and burns the fuel, spins entirely on its own shaft at wild speeds up to 10,000 RPM. Then, the back section, the power turbine that actually turns your generator, spins on a totally separate shaft locked at that 3,600 RPM. They are mechanically complete strangers. There is zero metal-to-metal connection between the two rotating halves of this engine. So let's bring this all together and see how this builds out your mental model. You can now confidently explain that this engine operates on the continuous, smooth stages of the Brayton cycle. You know exactly why that steel box houses a literal jet engine, an aeroderivative custom designed for an elite power-to-weight ratio and fast grid response. And maybe most importantly, you know that inside that casing, the hot core and the generator run on entirely separate rotating shafts. I'm going to leave you with this provocative thought to ponder until our next explainer. If the jet engine core and the power turbine generator don't actually touch, and there is absolutely no physical metal shaft connecting them, what invisible force is transferring 30 megawatts of spinning power from one side to the other without losing a single beat? Think on that for a bit, and I'll see you next time as we crack the casing wide open to find out.